Hi. So thank you very much for coming to my talk. I hope you guys have been enjoying DevConf. I'm sure some of you might have struggled to wake up this morning, but those of you who do, or who have done, well done. So a bit about myself. I'm Sam. I've always been an engineer coding all sorts of languages, and the inspiration for this talk actually happened during a conference where I was always doing web engineering, .NET engineering, building web APIs, building websites, JavaScript, and then I sort of transitioned towards big data. And the inspiration of this talk was to share my experiences, what I learned, and hopefully give you an idea of all the concepts that I had to painfully learn. Out of interest here, how many here are, would you say, traditional engineers building websites, even QAs? Yeah, OK. Most of the room. And how many are actually thinking of transitioning towards a big data role? That's OK. At least some people are interested. That's good. So I think the first question you sort of ask yourself is why? Why did I move? Why did I change careers? And I mean, it dawned on me that the unique selling point between company A and company B isn't their tech anymore, isn't their features, isn't their UX, but it's their data and how they use their data. And companies like Google and Facebook have been doing this for years, really, but only now are companies realizing the wealth of data they have and how it's beneficial. As an example, WhatsApp and Instagram, they were sold for billions, not because Facebook couldn't create a chat app or couldn't create an image filter, but it's because of their data and understanding their customer behavior. And that's sort of why in transition, I saw that there's a unique selling point there, and I really would like to help companies build and understand their customer behavior and build data-driven products. A bugbear of mine was how sometimes you'd build something based on an assumption. And that's OK, because in IT, everything we do is assumptions, every single thing. We assume if we do A, we'll get B, or we'll profit from X. But it's really painful when I don't know if any of you have this experience where you go and you build something and you're really proud of it. It gets out there in production and it's virtually never used. And that's the last thing I built as an engineer doing web development. I built something that was requested by marketing, and it went out there in production, and I think 6 months later, it just got archived, never got used. And a good example of this is, you can Google this, 50 Shades of Blue, has nothing to do with the book, but basically, and a marketing executive, it's been attributed to Marissa Mayer, which I read it before it became attributed to her, so I'm not quite sure if it's true. But basically, a marketing executive at Google said that they want to change the color of the Google Ads background to a different shade of blue. And the engineers of Google weren't really convinced at the time, so what they did was they deployed that shade of blue, but they also deployed 47 other shades, slightly different. And the way they make the money is when people click on the ads, and they realize that if they were to deploy the original shade of blue that the marketing executive requested, they would have lost millions of pounds throughout the year. So that's kind of a good example of how data can be really beneficial when you're building something. That's just basic A/B testing, but it's really powerful. So what is big data, right? And I really like this tweet, and I've kept it for so long, because everyone comes up with this idea of what they think big data is. And out of interest, how many of you here think like 100,000 records is big data? 1 million? 10 million? 100 million? There are different definitions I'll go through, but I go with the most accepted, which is, they're basically 3 Vs, right? And the first one is volume, the size of your data. We're talking about hundreds of terabytes, a petabyte scale. When people would classify as big data. Things that you can't really handle on a single machine. It needs to be distributed. The next type is velocity, how fast this data is coming through. Is it a record a minute, a record every half a minute, a millisecond, a nanosecond, how fast this data is coming through your pipes. And the last thing is variety. How many different data sources, how many different data points that you have. Things are coming from Google Ads, your tweets, your shares, your marketing. How many different data points are telling you about how people are using your product? And the first thing I had to learn very, very fast was what ETL is, because it's like the bread and butter to what big data is. It's moving the data around. What ETL stands for is extract, transform, load, which is taking the data from a data source, extracting it, transforming it into a shape that your business understands. So for example, it will be called a payment reference somewhere. It could be an order ID somewhere else. And you need to shape it in a way your business understands. And then you load it into, preferably, a data warehouse. Now, a difference between a database and a data warehouse is a database is sort of been designed or geared for transactions. So it's a difference between OLTP and OLAP, and online transactional processing and online analytics processing. But in layman terms, it means that it's a database designed for writing, which is what most websites use, and a database designed for reading, which is what the analytics use, 100 more reads than writes. And that's the point where I was drafted into my team. I was supposed to lead a team of data engineers of where I work and move them to where they were to a more robust and scalable data pipeline. So to give you an idea of what was happening was they had a lot of Python scripts hard-coded into a Windows box on AWS. And this thing was extremely painful to maintain. It will fail every other week if they were lucky. It would take forever to run, and it's hard-coded to that Windows box. And AWS would just restart this box once a month for security. And at the time, we thought, well, that's really annoying. And then the NHS happened, and we realized how important those security updates were. So it was really difficult to maintain, and we needed to deal with it in something that's more maintainable and more sane for us. Another thing was new sources were extremely painful to have. Now, previously, as all websites are, they start as a singular monolithic website, and then it gets split out into little services to handle the scale better. The problem is, when you split it out, the data sources that these services have become localized. They have their own read model. And for example, let's say you have a website and marketing come in and say, look, we want to implement Facebook login because then people don't have to sign up. It lowers the barrier of entry. So what happens when you've got a website that is scaled out and has hundreds of services dealing with every single thing, people who implement this social login or Facebook login implement it within their service. It becomes within their data model. And the ETL team, who are handling the original single source database, which was originally the single source of truth, would not have that. So people go to BI and say, look, we've implemented Facebook login. How did we do? How many orders were Facebook orders, for example, compared to how many weren't? And we were like, when did we implement Facebook login? So there's a massive communication problem there. And we have to actually go and chase the team who implemented it and understand where they put their data and then get it in. And it was extremely painful because these data sources now are different. There used to be a SQL database. Now, people are talking on MySQL, Dynamo, Redis. There's so many different data sources we have to implement. So adding new sources was extremely painful. Another pain was it took forever to run. Like it took 9 hours to run on a day because we had 18 countries we were ETLing. So 18 different databases, or 18 different environments. Each of them will have multiple databases. So it took 8 or 9 hours to run, and it was extremely painful. And the painful part was, if it were to fail, and it used to fail every other week, even if we fix it within 10 minutes, within 5 minutes, it will take another 8 or 9 hours to run that data load, and that's the whole day. It's a write-off. And that was really, really not good for the analysts who come in and say, well, we've got no data for yesterday, we've got no data for the weekend, we don't know how we did. And we need to, the dashboards are not updated, for example. So we came in and said we want to build a data pipeline. We want to build something that's really reliable more than anything, scalable, and it'll handle everything. And our underlining goal was to make sure that the data is queryable. Whenever there's a new data source coming in, whenever there's new sort of data, whenever there's, we inherit or we acquire a new company, we want that data queryable. And we wanted to, because that's when you get the value from your data, when it's actually, when analysts are able to read that in and make assumptions make valid assumptions and understand how the customers are utilizing the website. The other thing is we need to handle bad data. And that's another painful thing. You think moving data from A to B is easy, but then what happens when you're expecting something to be a timestamp and it's a different version of timestamp? It's in UTC, BTS, it's a string, it has weird characters in it. You expected something that's a number, came in as a Boolean, for example. So you just need to be able to handle this bad data. And it's one of the painful things. And we need this pipeline of ours to handle it very well. We needed to allow schema updates to be extremely frictionless. So before, people would tell us, look, we've got a new column coming in, or a new field, because it's an API, and you need to call APIs that returns JSON. And it's a new field, and technically that becomes a new column in the data store. And we were lazy engineers. We needed to make sure that we're able to handle it flawlessly, and we're never in a situation where people tell us, look, there's a new field that allows Facebook login, you need to query it. And I was like, well, we didn't know that. We needed a pipeline to handle it effortlessly. So we also want to add alerting. So when it fails, everyone is aware. We wanted to add dashboards. These are the basic core concepts of DevOps that I'm sure everyone is aware of. And we want to make sure everyone's aware when there's an issue, when there's failure, the team's on the ball. There's also different data formats that we need to handle, right? So CSV and JSON, everyone's aware of it. It's easy. Everyone's fine with that. But then what happens when you get you can open it in your computer. It's very easy to see what's the problem with the data if there's a problem. But what happens if you get a 20 gig JSON file, for example, or a 20 gig CSV file, which is normal, right? People can't open that in their editor. People can't open that in Excel. So we needed to handle different data formats, and that's where Parquet and Avro came in. And the difference between them and traditional data formats is they're stored in columnar storage. And for those of you who don't know what columnar storage is, you save the entire column's data rather than the row of the data. And you do that because it then gives you a lot of compression. So all the one column will have all the same data types. It's one timestamp. It'll always be a timestamp. It's an int. It'll always be an int. It's a string. It'll always be a string. So the amount of compression that you do is a lot higher, hence making the file smaller and much more manageable and easier to handle. We also added Apache Spark. Apache Spark needs its own talk, but a lot of my demo will be based on Apache Spark. But the two core things that Apache Spark gave us is the fact that it's a distributed cluster that handles data, and it handles multiple data formats, which is one of the key things that we wanted to do. But it also allows the entire business to look at the same data and handle it in different languages. So it does Python, so that's PySpark. It does SQL. It does Scala for us, and then R for the data scientists. So you can query, you can talk about the same data and query it in the same way or in the same engine. And that's extremely powerful because then it allows people to share their code and understand how they're querying this data. And then it makes it easier to productionalize things like data models and machine learning models. We also wanted a workflow manager. Now, we had to implement a workflow manager because traditionally, these hard-coded Python scripts will handle things like scheduling, alerting, and it was extremely difficult to actually reason about what exactly this code's doing. A workflow manager that we implemented was Airflow, which would handle the heavy lifting and say, look, I'm going to tell you what to do. I'm going to tell you how to do it. I'm going to tell you where in the code to do it. And then also, I'm going to add things like retries and alerting and scheduling and retry backoffs and delays. between, try it again, because the data, for example, is not there if you're on time-based, or if you're on event-based. It allows you to just free yourself from handling this really complex problem. This is Airflow. You can use something called Luigi as well. They're designed to do that. In a very simplistic way, it's cron in the UI, but it also adds things like alerting and monitoring. We also had to add a data serving layer. Now, our data serving layer was Redshift, and that's pretty much the de facto data warehouse that you see in most places, right? Because it's distributed, it's based on PostgreSQL, and then Amazon took it and did stuff with it, and it's very, very resilient. The problem we faced with Redshift was the storage and the compute were together, and that's with most databases. That's a problem because you can have your dashboards running off Redshift, mostly Tableau, but Redshift. You've got your data scientists querying the entirety of the history of your data, and then you've got people like your ETL loads are running all the time. And they're all sharing the same space, and they're struggling to make things work. And it's very difficult to have a conversation with your stakeholders and say, I'm sorry the dashboards are not up to date, but it's because some data scientists are querying the entirety of data. They're completely separate concerns. But Redshift doesn't allow you to. You have to scale up both together, and it becomes very, very expensive. And sometimes we don't need that cluster running all the time. So we wanted to separate the compute layer, which is actually doing the heavy work, and the storage where the data is stored. So we used S3 as our data lake. We put all our data there, store it as Parquet, and then have Presto looking into this data and assign a schema. And the difference between a database and a data lake is schema on read and schema on write. So with Redshift, when there was new schema updates, what you normally do, and what you normally do with all databases, is say, actually, no, alter this table, add a new column, and now it's just null in the past, and it's now required for everything in the future. With NoSQL databases, that doesn't exist. You're putting the entire blob. But with S3, it's flat files. And it doesn't matter how this data comes in, because we have no control of how it comes in. We only have control of what to do after it comes in. So obviously, we needed to add a data saving layer. So we had Redshift for the dashboards. We had Presto, which is what Athena is now, AWS Athena, where you define a schema and say, this is where the files are in S3, and you make it queryable. So we're able to run SQL against it. We want to implement a Lambda architecture. And what Lambda architecture is basically is we've got things like a hot and cold path, where you've got the batch layer, which runs once a day, where you've got data providers that only provide your data once a day at 3 a.m. or 2 a.m. And then obviously the streaming layer for things that are running within seconds, within microseconds. And that's really powerful. The streaming layer is really interesting because it really can change the behavior of your customer. So you come, for example, if you've ever used something like hotels.com or booking.com, and you had to look at a room, it will tell you how many people are looking at this room and how many people are interested in buying it. We were in the fast food delivery business, it's Just Eat, and what we do, what we actually did was when someone looks at a restaurant and you don't know what you want to order from it, it tells you how many people are looking at this restaurant in your area and how many people would like to order something in your area. And it tells you, oh, look, this dish is really interesting because there's 10 people who ordered it in the past 5 minutes. So things like popularity to give, it's not exactly a recommendation, but it's more of a, this is what people found interesting, you might find interesting too. And that's what the power of streaming does. It can give you what's happening exactly in what the customers are doing on your platform in near real time. This is basically an example of streaming. It's like data always flowing in through a pipe. The issues we had with streaming when we implemented it is we had to actually build a proper scalable streaming platform. We had to implement Kafka. The problem with that is Kafka isn't something that it's not a service that you just pay for. You have to build it into your entire operation. You have to have people managing it. you also have to ensure, and this is the most difficult part, all your data is going through Kafka. Otherwise, what's the point? You want to expose everything to your business. You want everyone to be able to read this data, make it queryable for everyone, so BI or business intelligence aren't the blocker. However, you have to ensure all the engineers or all the teams are actually going through. That was one of the most difficult things we faced. And I remember going to a conversation with CTO and saying, well, actually, we need about 100 grand for a quarter to implement this. We're hiring, and we also need it for building and making sure that the data's going through. And they were like, no, because you have to prove the value of it. That's the problem, right? It was quite a heavy cost. So that's kind of why Spark came up with the idea of structured streaming, where they will continually monitor a blob storage or S3 or HDFS, and it will stream anything that's new coming in. It's like a file watcher. But the powerful thing is, it allows you to run SQL queries on the streams, so actually let you know exactly what's happening before you even store it to somewhere. And this is powerful because then you can run SQL queries to say things like time-based queries to say, what are the most popular things running right now who have had more than 100 orders, and boom, you've got like a table of top 100 restaurants in your area. So it allows you to run SQL queries on streaming data, and that's really, really powerful. Also allows you to save it to a different data store whenever you want, and that's basically why they implemented it. They realized that their customers, the people who use Spark, don't actually just write streaming queries. They actually do stuff with them, and this is their attempt to make it easier for them. The caveat here is it literally just got released into production, and the problems we faced with it was the fact that some of the whole goal of structured streaming was to unify the batch model and the stream model, and some of the operations, so some of the functions that you use, like drop duplicates, for example. You read the data frame and you drop the duplicates, were missing from the structured streaming, but it's very, very much quickly being patched. So we used it initially because it was marked as beta. We initially used it for the low risk logging to ensure it can handle the scale. Will this thing work in production if we use it quite heavily and rely on it? And it did. It had no problem with the scale. It's more of the operations or the functions that you would use on the batch layer, which we didn't actually have a lot of. Those actually were meant in the data model, and they were not used in streaming. It was streaming. It was just put something in, run a query over it if you need to, and then put it out. We didn't do any heavy lifting in the streaming. We then quickly realized that Redshift was not fit for purpose because a lot of our data became JSON blobs. We'd talk to APIs, we'd ask them to return things, and we'd ask them give us an ID. It was just RESTful APIs, and they return JSON blobs. And now running that and saving it to Redshift was problematic because it just didn't do it very well. And that's kind of why we came with Google BigQuery. Out of interest here, who has heard or have used Google BigQuery? Okay, good. So you saw I won't have to preach about it. It's a pretty powerful engine, and what it does is it's hundreds of thousands of Google machines that you save your data to them, and you only pay for the costs of your query. So you don't pay for the storage cost, basically, or you pay very little, 0.08 cents or something. But the difference is we're paying about £20,000 for Redshift a month. So there's a big, big difference. However, it cost about, I think, $5 for querying 30 gigs of data. So it was very, very easy to stream data into it, and you're able to validate whether it's useful or not at a very low cost. The cost obviously will escalate the more you push into it, but I remember pushing we queried about 4 terabytes worth of data, and it was still free because it's up once you get 2 terabytes free, and then it's like $5 for the extra 5 terabytes. I'll get you the cost later. The point is, it was a lifesaver for us, and it really helped us achieve that underlying goal of make data queryable as soon as it arrives as flat files. we realized that there wasn't a connector for Spark and BigQuery. So this is like, I ended up writing one, as most engineers do. And the GitHub is there if you ever want to push stuff from Parquet files or CSV or JSON in Spark, in Apache Spark, and write it directly to BigQuery. So it's kind of why I had like a humble brag about it, because like I quickly realized that people use it and are raising issues. And I'm the only one handling them right now. So feel free to help and contribute. This basically helped us write machine learning recommendations. Now, the first machine learning recommendation model I built was based on what people buy on the website. So say, for example, we had website A, right, that sells women's clothes. And I like to dress up as a woman on the weekends, right? And I have used this website for about 3 or 4 months. And I've bought 9 things. Let's say another person around my age has bought 10 things. Then, if the 9 things I bought are the same as the 9 things this other lady has bought, then we have the same taste. So the 10th thing that she had bought would probably be something I would be interested in. So it's very similar to Amazon's people who have bought this have also bought that. And that basically helped us tell people, look, you seem to like a certain type of curry. People your age in your area have ordered this. Would you be interested in ordering this? And it was really powerful because people come in and they're like, I'm not quite sure I'm hungry, I don't know what I want. And I look at what other people's tastes are, similar to mine, and it gives them a good idea. So now to the demo part, and I give you an example of, if I just go back to this screen and then limit, mirror these screens. There you go. That should work. Yeah. So over here, you can't see it, can you? So can I zoom in? All right. So I've got a JSON blob here, and we're going to assume this folder is my data lake, and it's filled with all the data that my company has ever had. And this is an example of a JSON blob. So I'm just going to open that. Let's open it with BB Edit so you can see. Right. Still not great. Can I zoom in here? No, I can't. So, all right, fine. I've got it open here, right? So this is an example of a JSON blob. I definitely can zoom in here, right? So this is JSON blob with nested JSON, right? And this is an example of what an API response would be. And you come in and you're like, OK, this is what it responds. Traditionally, what you do is you'd have to read that JSON, convert it into what's called a data frame, so it's like a table, and then save it somewhere. With Spark, what it does is if I switch to IntelliJ there and you look at my code, I'm sure you can zoom in here. Oh, nope, can't zoom in there. Oh. Of course, multi-zoom. So what I'm doing here is I'm telling Spark to constantly read the data lake folder, and then anything that comes in, I want you to use the connector to save it to an output sink, which is BigQuery. The really cool thing is you can also add a checkpoint, so it knows where it left off if it fails. So you can rerun the query, and it will just save it. So what we're going to do is, what we're hoping to do is run this. Can you zoom in here? Yeah. So what I'm hoping to happen here is I've got Google BigQuery open here. There is no demo table in this schema. So that's called a data set, and there's no demo. And what's happening here, according to the code, is I'm going to read whatever's in the data lake, whatever is in S3, and there's no schema here because it auto-infers the schema from the JSON blob. And I'm going to save it to a table called demo there. Okay, it's really not that much code, and it's on S3. But all it's doing is read data lake, save it to that table, and await termination. So kill the query. So over here, if you look at what's happening, is it's a lot of stuff. But over here is saying, look, I read some JSON blob, and this is actually the schema of the JSON. And this comes with Spark by default, right? It's not something you have to code. And then it creates the table somewhere there. And now the query is running. So if we go into BigQuery and refresh this page, and hopefully, if the demo is not too far, there you go. So I'm going to zoom out a little bit. So this is actually an actual table of the JSON blob. It's exactly the same JSON, but now it's queryable. So I could go into this table and say, give me, let's get something that's nested. Give me the user agent from whatever was in the JSON. And this is just simple SQL that your traditional analyst can run, right? And there, it's Mozilla iPhone. So if we jump back to the JSON blob, there, that is it. So, OK, fine, we achieved the point where we're reading from a blob storage flat file and make it queryable via SQL. But what happens if we then we've implemented a Facebook login, and now the API is returning a new field, right? So this schema here, if you look at the number of columns on the table, there is no Facebook login anywhere, right? This is all the nested blob, and it's just not there. So let's say this new file comes in, or we queried the APIs, and we're returning new column types. Traditionally, we'd have to go append the table, change the table schema, and start importing it. So what I'm going to do is kill that, copy the second file, there. So that's the second file that has the new column type. And I'm just going to restart that query. Now, it should already know that it's saved one file, so it knows where it is in the blob storage. And if we look at there, you'll find out that the last transaction saved was there. It's moved too fast, but there. The last transaction saved was 0, as in it's 0-based. And if we look at Google BigQuery again, and we query that table, right? The number of, if you look at details, there was one record, so hopefully, if I keep refreshing, it will pick up the new file too. Now, if I look at the schema and go all the way to the bottom, you've got the new column. And you look at the preview, all the way at the end, is Facebook login. It's null before because it never existed, but then it altered the schema automatically to add it. But then you sort of ask yourself, OK, fine. If we look at star, for example, and it will tell you how many, what the size of the data is. Fine, let's look at customer ID, right? And it said that it ran 16 bytes. That's not exactly big data. Right, OK. What if we query the entire history of GitHub, right? There. So I will query every single commit ever made on GitHub by myself. And I just want 10 records. So let's have a look about the size of this data. Oh, there you go. That's fine. Boop, 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 boop. There. Open that query and run that. Let's see how many. Oh, it's cached, so you don't actually run the whole thing. OK, fine. Let's add author so it doesn't cache. There. So it should, again, 27 gigs. Still not quite big data yet. Yes, run that. All right, the cool thing about BigQuery is it should always return within 10 to 15 seconds, regardless of the size of the data. And over there, I've just queried 725 gigs in 3 seconds. So it's really, really powerful to use, and I still haven't paid more than $1 here. So yeah, so for me, what my definition of big data is things that cannot be handled in a single node, but it also needs to make it queryable to give value to the business. And that's the end of the demo. So if you have any questions, feel free. But if not, thank you very much for listening to me.